The picturesque town of Stamford has been the home of the Blackstone Company and its predecessors since 1837. In those early days, production was, in the main, barn machinery and harvesting equipment. By 1896, the company had become involved in the manufacture of the oil engine, and today this remains their main product, but the emphasis is now on engines of a multi-cylinder, turbocharged design. However, the story begins not at Stamford, but in the heart of the Sussex countryside, 100 years ago. The little hamlet of Newpound was the home of the agricultural engineers of Carter Brothers. Today, a small part of the original Carter works still remains, although this building is no longer used in conjunction with the production of agricultural machinery. Brothers Frank and Evershed, seen here with their mother, pioneered the development of the Reliance oil engine in the mid-1890s. 3 sizes of Reliance engine were built, 2.5, 4 and 8 horsepower. This particular engine, bearing the serial number 6, was built around 1895 and is believed to be the sole surviving example of the Reliance oil engine. Like other oil engines of that period, ignition was by hot tube with a continuous burner. The fuel was ordinary petroleum or paraffin as it is more commonly known today. This engine was exhibited at the Royal Windsor Show in 1898, where it was awarded a bronze medal for performance. It was at one such show in 1896 that the Reliance oil engine was brought to the attention of the Blackstone chairman. Upon seeing the Reliance in operation, he persuaded the brothers Frank and Evershed to take their engine to Stamford, where its development was to continue. Before the engine can be started, the burner must be lit, and for this a small amount of methylated spirit is used. When the spirit has almost burned away, a couple of pumps on the pressurized system ignites the main burner. Within a few minutes, fuel vapor, seen at the top of the burner, indicates that the ignition tube should be hot enough to start the engine. Once running, the burner is pressurised automatically by the pump which is driven from the side shaft. A small air vessel is incorporated to give a constant pressure at the burner. A friction drive governor, driven from the side shaft, operates on a hit and miss system which sprags open the exhaust valve. As the engine speed decreases, the exhaust valve is allowed to close. The rocker arm serves a dual purpose in also operating the fuel pump. The throw of the pump can be regulated by a simple adjustment screw. The inlet valve is atmospherically operated. Another unusual feature on the Reliance engine is the use of vertically split main bearings, which are held in place with horizontal bearing caps. The forged crankshaft is also typical of that period. This unusual garden roller features an engine of unknown identity, but from its crankcase design, it's almost certainly of Reliance origins. Built by the Carters brothers, the roller was destined for use on the local bowling green. By 1899, Blackstones were in full production of their own engines, based on the Carter brothers' designs. This engine, supplied on the 14th of November of that year, is believed to be the oldest Blackstone engine in preservation. It spent most of its working life powering woodworking machinery in a wheelwright shop in a small village just outside of Peterborough. Independent tests carried out by the Highland and Agricultural Society of Scotland showed that this style of Blackstone oil engine had the highest mechanical and thermal efficiency, resulting in the lowest fuel consumption figures of all the engines tested. These early engines are believed to have left the factory without any of the eye-catching linings seen on later engines. They were, however, finished in varnish in the best style by competent workmen. Major differences in design from the Reliance included the base, which had now taken on the distinctive Blackstone curve, and the main bearings and housings. These had changed to the more familiar sloping design, reducing stress exerted on the mountings. At this stage, an unbalanced forged crankshaft was still being used. Whilst retaining the continuous lamp and hot tube ignition, a redesigned vaporizer was fitted. The friction drive governor had been replaced by a more positive one, being gear-driven from the side shaft. Hit and miss governing continued to be employed, but now operated mechanically on the fuel pump and additional fuel valve. The fuel pump was of a similar style to the Reliance and came complete with fine adjusting screw. An atmospheric air valve, situated on the far side of the engine, supplied pure air to the cylinder. Available in sizes from 2 to 44 horsepower, engines could be supplied in stationary or portable styles, with or without the foundation fuel tank. All engines came complete with silencer and toolbox, which contained several spares including lamp, oil feeder, ignition tube and ram's-bottom type piston rings. Cylindrical water circulation tanks of galvanised iron were supplied for each engine, along with foundation and fixing plans for installation. Blackstone's guaranteed all engine parts for 6 months against breakages, providing such breakage was not caused by careless or unfair treatment and that fuels and oils had been approved as suitable. This particular engine, rated at 5 horsepower, weighs around 1.5 tonnes and when new, sold for £95. An unusual variation of the continuous lamp Blackstone was this twin cylinder with a double throw crank. With an explosion time to occur alternatively in each cylinder, this style of engine was said to have run with great steadiness, making it highly suitable for such duties as generating electricity. Rated at 1.5 horsepower, this is an example of the smallest continuous lamp engine built by Blackstones. Carrying the serial number 33029, it was built in 1902 and was installed to drive a single ram water pump. It supplied all the water requirements for a large household just outside the town of Maidstone in Kent, remaining in service right up until mains water became available. The burner configuration on this engine is somewhat different, with a pressure lamp being situated below the vaporizer, pressure being supplied from a freestanding tank. The fuel is pumped up to the vaporizer when sufficient time has elapsed for the ignition tube to become incandescent. A few turns of the flywheel and it's away. Governing on these smaller engines was by inertia pendulum acting on the fuel valve. As the engine drops below a predetermined speed, the valve opens to allow fuel to enter. four-step pump lifts fuel from the base tank up to the vaporizer, where it drops onto a hot plate, vaporizing it before it enters the combustion chamber. The continuous lamp pressure vessel contains enough fuel for several hours running. It was thought that a replacement flywheel had been fitted at some time in the past, as all Blackstone engines appear to have been supplied with curved spoked flywheels. However, this recently discovered works photograph would confirm that straight spoked flywheels were indeed used. Possibly, this was an application for pumping units only. Like all manufacturers, the Blackstone company was continually updating their designs, and between 1903 and 1905, the engine which became known as the standard model was introduced. This engine had a number of features which were to set it aside from its predecessors. Firstly, there was the new design of vaporizer, this being of the horizontal closed type with internal ignition tube. A timing valve regulated the point of ignition by cutting off the heated parts during compression. Air was still drawn from the base to the inlet valve. The fuel pump, however, was now driven directly from the camshaft and was of a simpler design. Balance weights were now fitted onto a machined crankshaft, and the cast splash guard had been superseded by one of rolled steel. Starting these standard engines was a fairly straightforward process, with a separate lamp being employed to heat the vaporizer. It took around 5 minutes to heat the vaporizer and bulb hot enough for running. The bulb cover vent was opened to allow the bulb to heat evenly and prevent the lamp blowing out. The vaporizer consisted of 3 concentric passages, the outer one for heating the air, an intermediate passage for vaporizing the fuel pumped up from the reservoir, and a central passage containing asbestos. When running, this asbestos was kept incandescent by the heat generated with each explosion in the cylinder. Using this system, the lamp could be extinguished once the engine was running. A timing valve, fitted as an integral part of the hot bulb assembly, regulated the point of ignition by cutting off the heated chambers, helping to eliminate pre-ignition and reducing the chances of cracking the vaporizer. Another major change was the Carter's patent governor mounted on the camshaft. It acted on the vapor valve, providing hit and miss governing. As the engine speed exceeded the norm, the cam operating the valve ran idle, preventing fuel from entering the cylinder. With fuel being pumped at a constant rate, an overflow chamber allowed excess fuel to be returned to the base tank. This standard engine left the factory around 1907 and still has its original lining. Engines of this period were available with either standard flywheels for general use or with a set for electric lighting purposes, which were in some cases up to 6 inches larger in diameter. The original toolbox is still in good condition. One difference on this engine is the position of the air valve, which is moved to the top of the cylinder and was operated by pushrod. It draws air from the cylinder support casting along a tube which has a choke flap incorporated. This flap was manually closed on starting, then opened when the engine fired. The timing valve fitted to these standard speed engines operated by closing off a vertical slot in the vaporizer. The slot is clearly seen here on this vaporizer removed for inspection. Another unusual feature of engine construction was with the cylinder head. The cylinder head bolts actually pass through the water jacket, providing even cooling due to less cast iron, but resulting in very rusty cylinder bolts. Many thousands of these engines were produced, providing one of the mainstays in Blackstone production. Blackstones introduced their vertical hot bulb engine around 1912 to 13 period to meet customers' need for an engine that took up very little floor space. Two sizes were built, 3 and 5 horsepower. Although different in layout, they operated in an identical manner to the horizontal engines. Both overhead valves were mechanically operated by pushrods. The vaporizer and shroud was similar to the horizontal engine, as was the blow lamp, the only exception being that it had then to be suspended beneath the shroud. The pushrods were operated by a horizontal camshaft, which was gear driven from the crankshaft. A hit and miss governor controlled the engine speed by regulating the frequency at which the fuel valve was allowed to open. The camshaft-driven fuel pump operated at a constant rate, supplying fuel to the overflow chamber, which also has a water injection device incorporated. These vertical engines were supplied with either one or two flywheels to suit a given application. An unusual feature is the semi-open crankcase, of which the fuel tank forms the lower half. A sight feed lubricator ensured the correct level of oil was maintained in the crankcase, while the main bearings were supplied with wicks from oil reservoirs. The small cast iron pot was for draining off excess used oil and held around the same volume as the glass oiler. When introduced in 1915, the S.F.C, or start from cold engine, was a totally new concept in engine design. It had been designed to meet War Ministry specifications for an engine capable of starting instantly and running on low-grade fuels without the assistance of a blow lamp or petrol. The S.F.C engine, although being of a lighter construction than the regular Blackstone, was, nevertheless, built to their usual high quality. To enable starting straight from cold, an air blast was employed to spray fuel into the combustion chamber. This air was supplied from a small compressor bolted onto the side of the engine and driven from an eccentric on the crankshaft. The ignition was supplied from a special trip magneto fitted with double magnets to provide an extra strong spark at the igniter points. The air compressor also supplied an air vessel with enough air for restarting when required. As the engine was not supplied with a fuel tank base, a standalone tank was provided, containing enough fuel for several hours running. For one reason or another, the S.F.C engine never caught on, and only limited numbers were produced. Blackstones continued producing lamp start engines, providing several variations. One of these were the portable engines, aimed mainly at farmers who had a need for movable power sources. These were available in a range of sizes from 2.5 horsepower up to 37 horsepower, in both standard and high-speed models. This 7 horsepower high-speed model was first sold in 1920 to drive hot drying fans on a farm in Hereford. The total weight of 2,900 hundredweight includes the portable trolley. Constructed from iron and steel, it provides a very sturdy base, and by incorporating the fuel tank also lowers the engine's centre of gravity. The large portables were provided with cooling from a circulating pump. This pump, being driven from the crankshaft, ensures a constant flow of water around the cylinder jacket. Cooling the water is achieved by letting it fall over a series of wooden slats inside the tank, where it collects in the base, ready for recirculating. The trolley was designed with steerable front axle and could be supplied with horse shafts if required. The extra wide wheels reduced the chance of bogging down when moving the engine. The silencer, built into the girder frame, was used to draw air up through the cooling tower, creating a forced draft which aided water cooling. This 4 horsepower high-speed portable has the more conventional thermo-siphoned cooling arrangement without a circulating pump. With the absence of the timing valve, it carries the patented water drip valve to help prevent pre-ignition. This is achieved by drawing water from the jacket into the vaporizer when under load. This stone grist mill would have been built around the 1890s by Blackstones for grinding flour, a job it is still capable of doing today. The standard hot bulb engine was used for many special applications. Here it is combined with a single throw ram pump. Note that the flywheel has been fitted on the side shaft side of the crankshaft to allow pump gear to be driven from the opposite end of the crank. The pump gears are machine cut to promote long life and quiet running. Powered by a 2.5 horsepower engine, this type of pump was capable of raising around 400 gallons of water per hour to a head of 178 feet. The stack holds a head of water which eliminates any flow fluctuation at the outlet. When used in such applications, the engine coolant would be taken up from the supply being raised. When this farm in Sussex recently lost its electricity for 3 days due to storms, it faced severe problems with the milking of the 200 dairy cattle. The only solution to prevent this happening again was to install a standby generator. In preference to a small modern unit, the farmer located and installed a 65 horsepower spring injection Blackstone, driving a 50 kilowatt alternator. The engine had up until recently been used in a commercial orchard in Kent. The spring injection design was introduced by Blackstone in 1923 to meet demands for a cold starting engine working on crude or residual oils without the use of compressed air for injection of the fuel. The spring injection system was both simple in design and operation. To start an engine of this size, compressed air was used. It was stored in a separate tank which could be recharged directly from the engine when running. Around 300 pounds per square inch of pressure was required for each start. Once the flywheel had been barred round to the starting position, the fuel could be pumped up through the fuel lines and the governor latched open for starting. The decompressor was then set on half compression and the engine air valve opened to allow the starting air to enter the cylinder. This action was timed from the camshaft to reduce false starts. The oil was pumped up to all relevant parts by the mechanical lubricator. Turning on the compressed air from the main tank turns the engine over, building up enough speed for the engine to fire. The air valve could then be shut off and the engine put onto full compression. Once the engine had reached its required working speed, the air start vessel could be recharged by opening the charging valve on the side of the engine. This was done by the starting valve trapping a portion of the exploded exhaust gases and directing them into the air vessel. This action was repeated until the pressure was restored into the starting tanks ready for the next time. Normally, cooling would have been achieved by large tanks, but here a radiator and fan driven from the crankshaft has been substituted. To avoid the necessity of draining down the cylinder in cold weather, an immersion heater has been incorporated into the jacket. This enables the engine to maintain an instant supply of power 24 hours a day. An engine of this type could be supplied as either left or right-handed, depending on the location it was to be installed into. Spring injections were available with either 1, 2, 3 or 4 cylinders with an inline configuration ranging from 6 up to 600 horsepower. With small spring injection engines of up to 100 horsepower, there was an additional method of starting if required. As well as compressed air and normal cranking, a tapered plug could be screwed into the side of the cylinder with a smouldering taper attached. This taper helped fire the first few charges until ignition became normal. The engine could be turned over by hand on half compression until ignition was obtained. Full compression could then be restored and full speed reached. This method of starting could be employed when the air start cylinder, for one reason or another, did not contain enough pressure. Once running, the air charging valve could be opened to bring the starting cylinder back up to pressure. The spring injection design was to become one of the leading models produced by Blackstones, with low fuel consumption and running costs and proven reliability, a fact borne out by the many engines still seen in service today. At first glance, this would appear to be an ordinary hot bulb engine, but when you take a second look, you discover several features that do not ring true. Built in the mid-1920s, this type of engine can only be described as a transitional engine, from the old hot bulb to the new spring injection diesel engines. Many aspects of this engine reflect those of the pure diesel. This situation, with a mixture of components being used in one engine, was not peculiar to Blackstones, for no engine manufacturer could afford to discard castings every time a new model was brought out. These engines may have been built to special order, where a customer insisted upon having a hot bulb engine, knowing the proven reliability of the earlier style. There are a number of points to look for. The air intake is now a mushroom shape with an integral choke, and a banjo-type oiling system is employed on the big end bearing. There is a trough to collect waste oil going around the base, and at the rear of the engine there is a long removable drip tray. As compressed air was used in starting large Blackstone engines, some means of initially charging the air vessels was required. For this purpose, Blackstones offered this starter unit, comprising of a 4.5 horsepower horizontal two-stroke engine driving a vertical compressor. As the engine was only needed for short runs, ample fuel was held in the small tank which gravity fed into the carburettor. The vertical compressor was capable of charging two 15-inch air bottles up to 450 pounds per square inch in 30 minutes. By eliminating the need for drive belts, this starter unit was ideal in situations where space was at a premium. In the 1920s, Blackstones offered a range of spark ignition, petrol and petrol paraffin engines. These came in sizes from 1.5 horsepower through to 7 horsepower. The efficient yet simple carburettor was used on all sizes of engine and required a fuel pump to supply fuel from the unusually shaped strap-on tank. The overhead valves are both mechanically operated by push rods. Hopper cooling was used on the smaller size, while others came with tank or radiator cooling. With the extra heavy flywheel and elongated base, it would suggest that this particular engine was supplied direct coupled to a generator. Introduced in 1933, the DB engine was a vertical start-from-cold diesel engine. The engine's fully enclosed design, together with its DB definition, earned this engine the nickname of Diesel Box. Available in sizes ranging from 3 to 11 horsepower, they were supplied in great numbers to engineers and contractors who required an engine that was both reliable and simple to operate by unskilled labour. The DB engine was also a popular engine on direct coupled generator sets. With the cylinder cover removed, the horizontally opposed valves and injector are clearly visible. This works photograph shows the small DB engine on the production line. Today, under the title of mirrlees Blackstone, the company remains one of the country's leading manufacturers of the large internal combustion engine. Engines produced at Stamford or in the company's other factory at Stockport can be found doing sterling service in many countries, providing power for high-speed trains, trawlers, tankers and countless power stations. Here in the heavy machine shop, the larger castings are machined before progressing into the assembly shop. The capability of producing all their own castings has enabled Blackstone to remain in the forefront of engine manufacture. The foundry, with its flowing molten metal and showers of sparks, may give the impression of Dante's Inferno, but in reality it is among the most modern in the country. Before pouring, in this case a V16 K major base, the molten metal must be slagged off to remove all impurities. The crucibles, each holding 5 tons of molten cast iron, are transported to the mould using remote-controlled overhead gantries. Because of its size, the mould is sunken into the ground and requires pouring to take place from both ends simultaneously. As the mould fills, the gases are vented, and upon completion excess metal flows out and into the overflow reservoir. This, when cool, will be recycled. A casting of this size will take around 10 days before it is lifted from the mould, and a further week will pass before it is cool enough to be worked upon. After sandblasting, the casting will be stress relieved before being fettled. In latter years, production at Blackstone's has concentrated on the multi-cylinder inline and V-formation engines, from 180 to 4,000 brake horsepower. With an ever-increasing demand for higher specifications in industrial and marine situations, engines undergo rigorous tests before being commissioned, thus providing power units built with reliability and endurance. Constant development of test equipment and facilities has enabled Blackstone's to remain among the leaders in engine production, just as they were 100 years ago.